Okay, so trigonometric proofs. We have an exam next week. I think it's going to be on Thursday of next week. I just have to double check that. And this exam, success on this exam relies heavily on your ability to work with algebraic expressions that are trigonometric in nature. And that can be tested in a number of different ways. I can just give you a trigonometric expression and say, what is an equivalent trigonometric expression? I can give you a trigonometric expression and ask you to find the non-permissible values for it. Or I can ask you to do a proof. And I will tell you right now, everybody, and I'm not trying to be a difficult person with you, but I can tell you right now that if you write that exam and you want to rewrite, I'm going to want to see your work, and I'm going to expect to see a voluminous amount of work. I'm going to expect to see that you've been working on these things. You've been doing proof after proof after proof. Somebody who does the minimum amount, which would be page 314, 1 to 8, 10 to 13, and 15 to 18, that's fine if you understand it 100%. But if you struggle and struggle and struggle through that problem set for practice, and then you go, oh, whew, I'm glad I'm done that, and then you forget about it, you're not likely to do very well on the exam. And again, I'm not trying to be difficult. I'm not trying to be intimidating. I'm not trying to scare you. I'm trying to motivate you. That this is, you've heard practice makes perfect. Practice, 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 practice makes perfect here. This is because it's so new to you. Okay, so that's why we've got an extra day, including the seminar today, to work on these. So let's start with page 314. Does anybody have any questions you would like me to go through? Go ahead, Jonathan.
Question 11.
11? Okay, so everybody, your book should be open. You should have a formula sheet out. You should also have and I will open this other document as well. You should also have the pink sheet out that I've given you that gives you the suggestions to follow. There we go. When working with trigonometric expressions. Things like convert everything to sine and cosine. Factor if at all possible. Bring multiple fractions together with a common denominator. Keep your eyes peeled for identities that you're familiar with. And the last thing, of course, is it's really common sense. If you start to get into trouble, most of the time, if you start to get into trouble, whether it's with a math problem or anything else, you don't keep moving forward in that direction, right? You maybe rethink your decisions and go back to the beginning. And then when it comes to proving identities, of course, let's not lose sight of the fact that when you're proving an identity, you want the left side and the right side to be equal to each other. So Jonathan, you said number 11, but can you be more specific because there are multiple parts to number 11? B, thank you. So we're asked to prove this identity, cosecant squared plus secant squared equals cosecant squared times secant squared. That's a very bizarre statement. There's probably not too many things in mathematics that are true like that. That's saying A plus B is the same as A times B. So what would happen if we took the approach, I'm going to work on the left-hand side independent of the right-hand side here. What would happen if we took the left-hand side and we rewrote everything in terms of sines and cosines? Well, what we would get is 1 over sine squared plus 1 over cosine squared of x. And that's the left-hand side. Don't forget, we don't write equals here, right? What we're doing is we are working on both sides separately from one another. Okay. Now, when you do this, Jonathan, what we end up having are two fractions with different denominators, so we need to bring them together with a common denominator. And the common denominator here would be sine squared of x cosine squared of x. And I would need to multiply and it occurs to me that maybe I should give you a piece of advice here. That when you write the stuff out, leave space. Like don't cram it all together, spread it out. Because what I want to do is I want to convert both of these fractions to the common denominator. And that means when I look at the first fraction, I'm going to have to multiply the top and the bottom by cosine squared of x. Jonathan, what will I have to multiply the top and the bottom of the second fraction by? Good, by sine squared of x. So that way, this fraction now is over, the fraction on the left is over sine squared x, cos squared x, and I'm left with cos squared x on the top. And then this fraction is going to be sine squared of x on the top. By the way, as I'm going through all of the work today with you and showing you and demonstrating you proofs, I'm not going to be writing down the identity names. We should have written in this first line reciprocal identities, and that's what you would have to write on an exam. I'm not doing that. Okay. Now what we can do is we can say that the top of this expression is 1, and we would put Pythagorean identity there because cos squared plus sine squared is 1. Does that make sense? Okay. And if I like the fact that I saw your eyes, you looked at what I just wrote, and then you looked up and to the right, you were looking at the other side of the equation, or the identity. And if we write this in terms of sine and cosine, cosecant squared is 1 over sine squared. Secant squared is 1 over cos squared. And if you multiply those two fractions together, you get 1 over sine squared of x cosine squared of x. Are you okay with that, Jonathan? Okay. Other questions? Ian? 3D. All right. Well, I'm not there yet. Give me a second. So 3D. Okay. So we have cosine of x over secant of x minus 1, and then plus cosine of x over secant of x plus 1. Now, changing everything to sine and cosine is not always the best thing to do. I can see, because I have more experience with this, that if I left it as secants, I think we might get there a little quicker. But you don't have that experience yet. So I'm going to rewrite everything in terms of sine and cosine. What are we going to have? We're going to have cosine of x. And all we're asked to do here, I'm seeing no equal sign. So I'm assuming all we're asked to do is simplify this. And what that would mean, Ian, is if this were a proof, you would have equals something and you would want to prove that they're equal, right? So I'm going to rewrite this as cosine of x, and then on the bottom I'm going to have 1 over cosine of x minus 1. And again, pay careful attention to how everything is lined up. There's some care and organization to how I write this. That the number 1 is 1 over 1, so I have fractions lined up nice and neatly. And then I have plus, I have cosine of x over, and then I have 1 over cosine of x plus 1, which is 1 over 1. You certainly don't need to write this. I'm just pointing out that I'm taking care to align all of my fractions properly. Because when we multiply fractions, we have certain rules. When we add fractions, we have certain rules. We need to keep the denominators separate from the numerators. What do we do with this expression? Well, what we're going to have to do, and as much as I gave you a suggestion here a few minutes ago, I didn't really follow it. The suggestion I gave you was that you should space things out, right? And I'm not saying at this point you need to erase it, but if this is a written response question, my next move here would be for this first fraction to multiply the top and the bottom by cosine of x. And we talked extensively about this yesterday because I want to get rid of this mini denominator. I call it a mini denominator. It's the denominator in the denominator that makes the entire fraction complex, which is not good. We want simple fractions. And I also want to get rid of this denominator as well. So that means I need to multiply top and bottom of this by cosine of x. So what do we get? We end up with cosine squared of x over 1 minus cos x. And I take back what I said a few minutes ago, which is that I have more experience, so I would do something different that would be quicker. I now believe that if I did what I thought I wanted to do, it might even be longer. Okay? Maybe. So this is a really good move, what we're doing here. Any questions with getting to this point here, Ian? Okay. So now I do the same thing here, and I have cos squared of x over, and I'm going to have 1 plus cos of x. And the only thing we can do here right now is to bring these two fractions together with a common denominator. There's nothing else you could do. When you go through that list, and you might take math at a higher level and realize that this list here is incomplete. There might be other things you would learn. But at this level, if it's not in this list, pretty much we wouldn't do it. So the only option we have here is to bring these together with a common denominator. And the common denominator would be 1 minus cosine x times 1 plus cosine x. And I'm deciding here to write these two fractions separate to begin with, and I understand that some of you would just prefer to put it all together in one fraction to begin with. And that's fine. But I'm not teaching to the high end of the class, I'm teaching to the whole class, so I want to make sure everybody gets this. Now we're going to do some multiplication here, but we're not multiplying to cancel. It's not like the green cos x's at the top of the screen where we were trying to cancel stuff. What we're multiplying by here is top and bottom by whatever is necessary to achieve the new denominator. So the new denominator has 1 plus cos x and 1 minus cos x in it. We need to multiply top and bottom by that. And over here, we need to multiply top and bottom by 1 minus cos x. So what am I going to have? I'm going to have, let's multiply this stuff through. I need to multiply that and that. So I'm going to get cosine squared of x plus cosine cubed of x. And over here, I need to multiply this, and I'm going to get cosine squared of x minus cosine cubed of x, which is a real relief, isn't it? That we're going to have cosine cubed minus cosine cubed. We start to see cubes into the fourths and stuff like that with trigonometry, and it's something we want to avoid if at all possible. So when I put this together, I get 2 cos squared of x over 1 minus cos x times 1 plus cos x. because what we're going to do here, Ian, is we're going to take this numerator and we're going to add this numerator. So we get, you see how that works. We get 2 cosine squared of x, and the cos cubes cancel. Well, they have a sum of 0. Now, normally, if this were, and you Math 31 students will appreciate this a lot, normally I would say leave the bottom in factored form. Factored is always better. But there's a reason why in this case we want to multiply out 1 minus cosine of x times 1 plus cosine of x. How many of you understand the reason why we would want to do that? What will we get if we do that, Marcel? I'm just talking about the bottom. If we FOIL out the bottom, what do we get? Try it. Yeah, go ahead. Right, 1 subtract cosine of x quantity squared. So we get 2 cos of x over 1 minus cos squared of x. And you should recognize 1 minus cos squared of x as sine squared of x from the Pythagorean identity. So now we have 2 cos of x over sine squared of x. Now let's just pause there. I don't know exactly what the question says, but that's certainly simpler than what we started off with. Okay. Just take a quick peek what the question actually says. The question says for us to express it as a single term. So we are done. A single term means you don't have something plus something. Yep.
3 fractions up on that same, on that same thing, on the top fraction. 2 cosine x squared, and then on the bottom. How come you got rid of it?
Are you saying are you asking where did this go?
No.
Oh. I got you. I have an error there. Is that what you were talking about? It still should be cos squared. I just didn't write it for some mysterious reason. Now, you again need to be aware of something, that when you take a look at this, which I'm going to call the answer, if it were a multiple choice question, it might not be that. It might be that. Because cosine squared over sine squared is cotan squared. That may even be the answer in the back. I don't know. You need to recognize that that could be also written as 2 over tan squared of x. That's possible as well. It could be written, and there is a limit to how many ways you could write this. This could be written as 2 cosine squared of x cosecant squared of x. Because cosecant squared is 1 over sine squared, which would put the sine squared on the bottom. It could be written as 2 cosecant squared of x over secant squared of x. Because the cosine squared of x is the reciprocal of secant squared of x. So instead of cos squared, I could write 1 over secant squared, and that would put the secant squared on the bottom. There's like 5 different ways that I've got this written. This is correct. 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 There's lots of different ways that you can write these answers. Other questions? See, to be perfectly honest with you, that scares me. That of all of this stuff that we've been practicing, or that I gave you for practice, there are 2 questions. There's got to be more questions. If there aren't, you haven't been doing anything. I'm not trying to be difficult again, and don't feel bad for this. I'm just pointing out this is the reality. If you don't have questions, that means you're not trying. If you're not trying, you're not going to be able to do well on the exam. You're not going to learn the material. So I'll give you a second to look over more work and see if you have any other questions. And some of you may have been doing a lot of work and you're doing it great. And if that's the case, I'm impressed. That's really good. But any other questions? Jonathan? 12A? Certainly. So we want to prove this identity. Now this is a unique situation that we haven't encountered yet, because all of a sudden we don't have secants and cos squareds and sine squareds and all that other stuff. We have sums and differences of angles. And the only thing we can do here, and I guess technically this isn't really listed here, but I think you understand that when I say keep an eye out for parts of any known identities, what I'm saying in a more general sense is use the identities to rewrite things into different forms. So for example, if you have sine squared of x plus cos squared of x, we rewrite it as 1. So how can we rewrite sine of 90 degrees plus theta? Well, I'm just going to write this up here so you can see it. And you're going to have to double check to make sure that this is correct, that sine of a plus b is equal to sine a cos b plus cos a sine b. Is that correct, Jonathan? Okay, so what that means is with that identity that's on your formula sheet, we can write sine of 90 degrees plus theta. So I'm working on the left-hand side here. I'm not rearranging or anything like that. I can write for the left-hand side sine of 90 degrees cosine of theta plus cosine of 90 degrees sine of theta. And again, I'm just working here on the left side. And this stuff on the right-hand side that I've written is I'm just writing down what's on your formula sheet. So I don't need to write this down in any of my work. I was just wanting you to see the identity up here. Now what we can do is we can put in numbers for sine of 90 and cos of 90, because these are known values. We know that, and we know that. These are known. Or maybe I don't have to say known. They're determinable. We can figure them out. And, you know, if push comes to shove, you can actually use your calculator and go sine of 90 degrees and get the number 1. But we should know that sine of 90 is 1. Because on the unit circle at 90 degrees, the y-coordinate is 1. And then we have times cosine of theta, plus we should know that cosine of 90 is 0, and then we have times sine of theta, which works out very nicely, doesn't it? Because the left-hand side then becomes cosine of theta. Because 0 times sine of theta will be 0. We can do the same thing over here on the right-hand side. And by the way, you would write here on the left-hand side some identity. You would describe the identity that you've used. Over here, we can use the difference identity, which will be sine of 90 degrees, cosine of theta, minus cosine of 90 degrees, sine of theta, and do the same thing. I'm not going to repeat by writing known. I'm just going to say that we know that this is 1. And we'll finish this in a couple of, I'll finish it now, and then we can take a break. And then we have cos of theta minus, what is cos of 90? Cos of 90 is 0. Sine of theta. So we're still left with cosine of theta, which means the left side equals the right side. Does that make sense? Okay, good. Other questions? That's why we're here, so. 7A? Certainly. So we want to prove this identity. Again, you take it's called the two-column proof method. You rewrite the right-hand side of the identity on the right-hand side of your line. You rewrite the left-hand side on the left-hand side of the line. One of the reasons why writing everything as sine and cosine in this example is going to bear fruit, it's going to be productive, is because there's no pluses anywhere. Right? You have a single term on the left-hand side and you have a single term on the right-hand side. When I rewrite this, I get 1 over sine of x, and it's over 2 cos of x. And you would put reciprocal identity there. Now you have a complex fraction, right? And one of these days I got to look up the name of this. There's a name and it escapes me. I always forget it. That main fraction line has a name. It defines the numerator and the denominator. But we see, because the numerator has a denominator, we want to eliminate that denominator. In other words, this fraction that's written in brown, Adrian, is a complex fraction. We want to simplify it by multiplying top and bottom by sine of x in this case. And when we do that, what's going to happen is these cancel, and we're left with 1 over 2 sine of x cosine of x. And, you know, maybe I should say to you, everybody, that when I say write everything as sine and cosine, what you want to do once you do that is simplify it until you can't simplify it anymore. We cannot simplify this expression anymore on the left, leaving it as sine and cosine. Well, we kind of can, but I don't want to go there just yet. On the right-hand side, we can write this as 1 over sine of 2x. And again, we would give a reason for that. We would say it's a reciprocal identity. And then, let me be clear here. When I say rewrite everything as sines and cosines, I mean sine of x and cosine of x. Sine of 2x is not written in terms of sines of x and cosines of x. But we have a double angle identity for sine of 2x. Sine of 2x is equal to 2 sine x cos x. And once you see that, you can see that we're pretty much done. Because if I replace that sine of 2x on the left-hand side using this identity, then I'm going to get 1 over 2 sine x cos x. And then we can say left side equals right side. Does that make sense to you, Adrian? Okay. How many of you, though, so we're done, left side equals right side. How many of you looked at this and said, oh, that's sine of 2x? You know, and that's the other option, is you can recognize that as sine of 2x, which means, you know, it's not really simplified. I guess this is simpler than the line above. And then you could even look at this and recognize that that's cosecant of 2x and not even touch the right-hand side. Is that good, though? Okay. Other questions? I saw other hands up. Go ahead. 18? 18 is a big number, so it's likely to be a beastly question. Usually those are at the end. Yeah. So we're asked to prove 1 minus sine squared of x minus 2 cos of x over cos squared of x minus cos of x minus 2 is equal to 1 plus secant of x. So this is a perfect illustration, everybody, of you trying, which means you're not just going to freeze. You're not just going to be like a deer in the headlights and stare at this question, hoping against all hope that something magical is going to happen, because it won't. There's too many steps that have to occur here for us to prove this. Let me rewrite it first. And there are a lot of moving parts to this question. So I'm going to start off with the simpler side, which is 1 over 1 plus secant. I can rewrite this. Arden, you had asked about this, correct? Okay. I can rewrite this as 1 over 1 plus 1 over cos x. And I would write down reciprocal identity if I were doing a written response. I can then say to myself, I really don't like, and you know, maybe like doesn't even enter into it. We don't want complex fractions. So I need to multiply top and bottom by whatever is necessary to get rid of the highlighted pesky mini denominator of cos x. That means I'm going to multiply top and bottom by cos x. And, you know, at this point in time, there's nothing really I can do with this once I simplify this. I'm going to get cos of x. I'm going to get cosine of x on the top over 1 plus, pardon me, over cosine of x plus 1. Because I'm going to take this cosine of x and multiply it by the 1, and the cosine of x multiplied by 1 over cosine of x. So you see how I get that? Okay. Now we're at the stage that I was at in the previous problem that was asked about, which is that it's written in terms of cosines and sines, and there's nothing else you can do with it. So that's kind of an ending point for the right-hand side. On the left-hand side, there are, again, moving parts to this. There's a number of different things that we have to recognize. One of them is that the denominator of this is quadratic. It's like a squared minus a minus 2. It isn't a squared minus a minus 2, but it's like it. And you should know how to factor a squared minus a minus 2. You would be looking for two numbers that multiply to give negative 2 and add to give negative 1. Those two numbers would be negative 2 and positive 1. But it's not a and a, it's cosine of x, cosine of x. Now, remember that on the back of that pink sheet that I printed off for you, the extra thing that you have to be aware of when you're solving, when you're doing a proof, is keep your eye on the other side. And I can see, you're not going to do this in your work on your proof when you're writing this out, but I can see that there's a cos x plus 1 in the denominator, and I can see there's a cos x plus 1 in the denominator. And that serves two purposes, recognizing that. One of them is it gives me a little bit more confidence that I'm on the right track. You know, as I figuratively say, the clouds are starting to part a bit and the sun is just poking through. Things are getting nicer. However, there's a cos x minus 2 on the bottom that we don't want, and there's a cos x on the top of the other side that we don't want. In order for us to, I'm thinking ahead here, I could just tell you what to do, and some of you might know what to do. But in order for us to cancel this cos x minus 2, I'm kind of being led to believe that I better have cosines only on the top. That sine squared of x is a real pain. And if we take, I believe it was Marcel who suggested the other day, his approach, he would recognize that this is cos squared of x. Was that you who were kind of doing that? There's another way to do it too. You could put, instead of sine squared, you could put 1 minus cos squared, and then you'd have 1 minus cos squared. I think your approach is more direct here. You recognize that 1 minus sine squared is cos squared, and the top of this becomes cosine squared of x minus 2 cos of x. I don't want to just dismiss the other method, because this method is not, as I said to Marcel and you guys yesterday, is not always viable, because maybe it's not 1 minus sine squared. Maybe the question says 2 minus sine squared. So the other alternative here is not to recognize that 1 minus sine squared is cos squared, but to say that on the top here I have 1 minus sine squared, and sine squared is 1 minus cos squared. So what I'm doing here is I'm substituting in, I'm running out of colors, I'm substituting in for the sine squared 1 minus cos squared. But what you're going to have here is the 1 minus the 1, which is 0, and then you're going to have minus a negative cos squared, which gives you cos squared. Do you see where to go from here? Yeah. So what you're going to do now is look at the top and factor out a cosine of x. You'll be left with cosine of x minus 2. And now, if the sun isn't fully out, figuratively speaking, it will be in a second. You should recognize exactly what's going to happen here. We have a factor. It's a factor because this is in brackets. We have a factor on the top and the bottom that is identical. Please, on a written response, don't just leave it like that and write left side equals right side. Rewrite this so that you have cosine of x over cosine of x plus 1. And then you can say left side equals right side. Is that okay, Arden? Perfect. You know, again, along the way, like at this stage where we went from here to here, you would have to write Pythagorean identity. When we went from here to here, you would have to write reciprocal identity, but you don't have to explain in words in any way algebraic steps. So multiplying top and bottom of the right by cosine of x, you don't want to explain that. It's not that you don't need to, you don't want to. You don't want to go down that road. Other questions? Ian?
Could you explain how you got cosine x minus 2 on the top again? On the top of a fraction, but it's on the bottom of the page.
How I got cosine x minus 2? Oh, I got you. You're wondering about how I got this? Is that correct? So, on the top of that fraction, on the top of that fraction, I have cosine squared of x minus cosine of x. If I had r squared minus r, do you see that I could factor an r out? Oh, sorry, and it's 2 cos x. Do you see how I could factor an r out here? If I factored an r out, what would I have left?
What you have on the bottom fraction.
No, I'm just saying if you had r squared minus 2r and you factored an r out, what would it become?
R subtract 2.
So if I factor a cosine of x out of this, what do I have left?
Cosine bracket cosine subtract 2. Thank you.
You're welcome. Arden, you had another question? 16? Definitely. So, wow, this is really pushing the envelope, this one, because of the 4x. And I would say to everybody that this is a question that the likelihood of you having to deal with this on a diploma exam or even my exam is almost zero. But I'm not just here for that. I'm here for my Math 31 students. And some of you are in grade 11, you might take Math 31 next year. Some of you are in Math 31 now. So we're going to use double angle identities to prove this. The left-hand side here, Arden, of tan of x is, we could spend some pencil time and write it as sine of x over cos of x. But why don't we just work on the big side, and if the big side becomes sine of x over cos of x, we know it's tangent of x. So what I'm going to do is I'm going to look first of all at the double angle identity for sine. But I'm going to change it. I guess I should use alphas here. And before I change it, I just want you to recognize, Arden and everybody, that this identity, it doesn't matter. It doesn't matter what this argument and this argument are, as long as they're the same. What matters is that this argument is 2 multiplied by this argument. And I know to some people, you may say, why are you writing that? I can see that. I just want to make the point that the argument on the left-hand side is twice whatever the argument on the right-hand side is. So I could write that, couldn't I? It doesn't matter whether it's alpha or heart or 2x. It doesn't matter what that argument on the left-hand side is, as long as the argument on the right-hand side is twice as great. So I can customize this double angle identity for any situation. I could even have, and we're going to encounter this in calculus, I guarantee you, I can even have this. Wrong. I can even have this. I can have sine of theta is 2 sine of a half theta cos of a half theta. So anyway, what I can do here now is for this right-hand side, for the sine of 4x, I can write 2 sine of 2x cos of 2x. And this is minus sine of 2x. I hope you recognize that there's a common factor here. And I don't know if we want to pursue that avenue or not. We're going to hold off on that decision until we're done with the bottom. Because if we don't factor out and maybe look at simplifying that way, the alternative is to rewrite those three pieces with double angle identities, and it's going to very quickly explode into a mess, which we may have to do. On the bottom, here's my thinking, Arden. Everything so far is in terms of an argument of 2x, so why don't I do to this the same thing that I did to the sine of 4x? So the difficulty here now is that cosine of 4x is equal to cosine squared of 2x minus sine squared of 2x. And I'm going to pause there to point something out. As much as I say the likelihood of this being on a diploma exam or my exam is almost zero, I think it's fair game that everybody understands that that's true, because that's a double angle identity. Even though it's not x and 2x, but instead it's 2x, 2x, and 4x, that's a Math 30 question right here. But cosine of 4x is also equal to 1 minus sine squared of 2x. And it's also equal, no, it's not 1 minus sine squared. It's 1 minus 2 sine squared. And the fact that I've messed that up from time to time, I think that's the second time in this unit I've done that and then I catch myself, means it's a very easy mistake to make. Cos of 4x is also equal to 2 cos squared of 2x. So the question becomes, of these three, which should I put in here for cos of 4x? Pardon me? Oh, I didn't get the minus 1? Thank you. Did I write it down? I'm just curious. I guess I didn't even write it down. Which of those three should I use? First, second, or third? 3. Right? Because the first two are going to have sines, and then I'm going to have this kind of mixture of sines and cosines on the bottom, which I'm working towards cosines here, because if I put sines and cosines on the bottom, I'm going to have 3 terms. I won't be able to factor it. But if I put 2 cosine squared of x minus 1, pardon me, cosine 2x minus 1, do you see that the bottom is now factorable? Or potentially factorable? I have to rewrite that bottom as, so let me write 2 sine 2x cos 2x minus sine 2x, and this is going to be over 2 cos squared 2x plus cos 2x minus 1, and then we're going to factor that. Now, we're going to have further to go here, Arden, because the left-hand side doesn't have 2x in it. But let's see if we can simplify the right-hand side before we dive into that pool where we have to change the 2x's to x. I can factor out of the top sine of 2x and have left 2 cos of 2x minus 1. Are you starting to suspect that maybe that 2 cos of 2x minus 1 is going to go away? Because the bottom is factorable as a quadratic, it's going to have 2 cos of 2x and cos of 2x. We're in a trial and error mode here. This has to be 1 and 1. And I believe if we do this and FOIL it out, it's correct. So what happens here is we're left with that. Okay, so now what do we have? Oh, goodness. Sine of 2x over cos of 2x plus 1. So the top of this is clearly going to be written, well, I shouldn't say clearly. It has to be written this way because that's the only way you can write sine of 2x using the double angle identity. So now, everybody, we are looking at the cosine identity for the bottom, but it's not going to be 4x and 2x, it's going to be 2x and x. And I think maybe I'd be negligent if I didn't write those down. We are now looking at over cos of 2x plus 1, and cos of 2x is cos squared of x minus sine squared of x. And I don't want to put that in for cos of 2x because then I get a mixture of sines and cosines, which is not really workable. On the other hand, cos of 2x is 1 minus 2 sine squared x. I don't want to put that in because then I'm going to have sines, and more importantly, if I put that in, I'm going to be left with 2 minus 2 sine squared x. I recognize that the third option is cosine of 2x is 2 cos squared x minus 1. And that's perfect because if I put that in, I will have 2 cos squared x minus 1 plus 1. The important aspect here is the 1 and the minus 1 go away. And I think you can see that we're going to get tangent here. I can tell by the look on your face. But let me finish this. We have 2 sine x cos x. And on the bottom, the negative 1 plus the 1 is 0. So we have 2 cos squared x, which is 2 cos x. Sine over cos is tan. Good? Other questions? Jonathan. 10b? Is that this one? So left side is sine x cos x over 1 plus cos x. And I may be wrong, but I believe this is a problem that has a wrinkle to it that we haven't encountered yet. I may be wrong. Over here we have 1 minus cos x over tan x, which I'm going to write as sine x over cos x, and I am wrong. The wrinkle that I was thinking of, we could use the solution to the wrinkle to solve this problem, but I think the wrinkle can be avoided by doing something different. And I'm not even sure I need to discuss the other option. I think we can always weasel and maneuver our way around the problem we're going to see here. The problem we're going to encounter here, by the way, happens whenever you see this kind of situation, where on maybe the bottom of one side you have a binomial, and that binomial is on the top of the other side, but it's the conjugate of the binomial. It's not the same. It's not a plus b, it's a minus b. Anyway, are you good to this point here? Okay. I see a complex fraction, so I need to multiply the top and the bottom of this by cosine of x. And what I get for the right-hand side by the way you would write quotient identity when you wrote down that brown work, is we might have to do this alternate thing. Okay, we'll see. We get cos x minus cos squared of x. We are going to have to do, I don't think we can avoid this little thing. Okay, so when you see these conjugates on opposite sides of the identity, and one is on the top and one is on the bottom, first of all, when we multiply top and bottom here by cosine of x, leave the top in factored form. Okay? And then we're left with sine of x here. Now, how are we going to make this work? The key, and this is going to be a little bit of a complicated thing to think about, but the key is recognizing that these two things which I'm going to highlight are conjugates, and if we multiplied them together, which we can't because you can't cross the equal sign in a proof, you have to work on both sides separately. If you multiply those two conjugates together, what you get is 1 minus cos squared of x, which is sine squared of x. So, looking over here, if I want to end up with a 1 plus, well, there's a couple of ways to do this. Let's do the following. Let's multiply the top and the bottom of this by 1 plus cos x. I better use a different color. And then I will show you, after we're done, I'll show you what the other thing is you could do. Because I just said there's a couple of options. One is to multiply top and bottom of this by 1 plus cos x. And I want to talk now about what that does. That does a number of things. First of all, I'm multiplying by 1. One of the things it does is it gives us a 1 plus cos x in the bottom, which is what we want on the left-hand side. The other thing it does is it's going to get rid of the 1 minus cos x that's on the top of the right side. We don't want 1 minus cos x on the top. How is it going to get rid of it? These two things multiplied together are going to give us 1 minus cos squared, which is sine squared. And you might even be able to see how this is all going to come together here. We have 1 minus cos x times 1 plus cos x, which is 1 minus cos x quantity squared. And then we have times our cos x. This is over sine x, and it's also over 1 plus cos x. We can rewrite the 1 minus cos squared now as sine squared and do a bit of canceling, and we should end up with that. And you might even see that, but I'll finish it off here. This 1 minus cos squared is sine squared of x, and then we have a cos of x. Then we have a sine of x and a 1 plus cos of x. One of these signs cancel. Just to be clear here, Jonathan, I'm going to write this up here as sine x sine x. So one of these cancels, and we're left with sine x times cos x over 1 plus cos x, which is what we had. Okay? I thought we could, as I say, weasel and maneuver our way around that, but I don't think we can all the time. If you wanted to, I said there's a couple of options. One of them is to say that this is sine x cos x over 1 plus cos x. We had already changed this tan to sine over cos, and what we ended up having was 1 minus cos x times cos x over, what did we have? Over sine x. So what I did in the method I used is I multiplied top and bottom of this by the conjugate of this to introduce that Pythagorean identity. I could have done the opposite here. Well, the same thing here, but multiply top and bottom by 1 minus cos x. When I FOIL this out on the bottom, and this actually might be quicker, I don't know, although we did do some work to get to here. I'm going to get on the top one minus cosine squared on the bottom. That's sine squared. What we've done is we've created 1 minus cos x on the top. We've got 1 minus cos x on the top of the other side. So this becomes sine x cos x times 1 minus cos x over sine squared x. One of the signs cancels, and you're left with the right-hand side. So there's nothing to say that you have to use one of the conjugates or the other. Is that okay, Jonathan? Okay. Other questions? Go ahead. 7b. 7b? Okay, so we want to prove this identity. The fact, Marcel, that on the on the left-hand side, there's a plus in between terms, means that most likely, you're going to have to be adding fractions together. But on the other hand, on the right-hand side, there's nothing to it. This is just 1 over sine of x, right? And as I've said before with this kind of thing, I don't think you even need to write that. I think you can just work exclusively on the left-hand side, and then if you get 1 over sine of x, you can write it as cosecant of x. Does that make sense? Okay. So, you know, writing everything in terms of sines and cosines is more often than not the way to go. Most of the time it's going to be helpful. And this is no exception. I'm going to write this as sine of x plus cos of x, and then it's times cotangent of x. Cotangent of x is cos of x over sine of x. And again, I know you know this, but it bears repeating. You would have to write quotient identity here, and on the right-hand side, you would have had to have written reciprocal identity. So what I have are two fractions. And you should know at this level that when you have something like cosine of x times cosine of x over tangent of x, it's really just one fraction because you're multiplying. And when you have multiple fractions being added or subtracted, you want to write them both over a common denominator, which in this case would be sine of x. So on the top of this fraction, we have cosine squared of x. And we're going to have to multiply top and bottom of this fraction by sine of x. And it's at this point in time that I think many of us see the solution. And you're nodding your head. Because the top of this is going to become sine squared. Sine x times sine x is sine squared. You know the next step is to put them together. And if you're like me, and I wish I could get in everybody's heads and see how you think of math. I think it would be a phenomenal advance in education, but we can't do that. in my mind, what happens is I say I'm going to put these together. And as soon as I say that in my mind, I see what's going to happen before I write it. I see I'm going to get sine squared plus cos squared. I don't have to write it down and then take a breath and look at it and go, oh, I make a decision as to what it is before. And of course, sine squared of x plus cos squared of x is equal to 1. So what we are left with is 1 over sine of x, which means we could say that left side equals the right side. And again, you would say Pythagorean identity or something along those lines there. I have seen people do proofs where not only do they write Pythagorean identity, they write the Pythagorean identity. You don't need to do that. If you do, be very careful that it's organized well. Other questions? Go ahead, Ian.
On this booklet, 5B on page 26.
Okay. 5B on page 26.
Yeah.
So this guy. A lot of work, but not difficult work. There's just going to be a lot of it, okay? So sine of A plus B, and this says prove? I just want to make sure, does it say prove? Okay. So it's a left side, right side thing. I'm not going to rewrite both sides. We can see what they are, right? So the left-hand side is sine of A plus B over cos of A plus B. Sine of A plus B is sine of A, cos of B, plus cos of A, sine of B. And then cos of A minus B is cos of A, cos of B, plus sine of A, sine of B. Okay. There's nothing you can do with that. there really is nothing you can do with that. Be very careful here because it's A and B, and it doesn't appear this way, but I want you to recognize if you had sine of A over cosine of B, you can't write that as a tangent, because you have two different angles, okay? So what are we going to do to the right-hand side? Well, the right-hand side, we've got a lot of stuff we can do. Cotangent of A is cosine of A over sine of A. I have a feeling I might need a little more room here. Is cosine of A over sine of A. Plus cotan of B is cosine of B over sine of B. And then, oh man, cotan of A is cos of A over sine of A. This is actually going to simplify pretty quickly, I believe. My whole discussion about tan of A plus B, I was being careless, and I just looked at the right-hand side briefly, and I thought it was cotan of A plus B. It's not. All I'm doing here, Ian, is using the quotient identity for cotangent. And then I can do the same thing for this cotangent of B, write it as cos of B over sine of B. So does that make sense, that step? Okay, I apologize for my digression. I have all kinds of stuff that needs to go. Well, you know, in reality, I only have two kinds of stuff that need to go. I need to get rid of the sine A's, and I need to get rid of the sine B's in terms of complex fractions. So I'm going to multiply the top of this expression by sine A, sine B. I'm going to multiply the bottom of the expression by sine A, sine B. Do you see you're going to get the left-hand side? If I multiply out the top, when I multiply this by that, the sine A's cancel, and I'm left with cosine of A times sine of B. When I multiply this out, the sine of B's cancel, and I'm left with cosine of B sine of A. Ian, do you see that that's the top of the left-hand side? The order that any of these are written in, I could, not that I have to, but I could swap these two and still keep the same meaning. Or I could swap this whole thing and keep the same meaning, right? So that thing that I have written so far on the right-hand side of my work is the top of the left-hand side. What happens when I multiply sine A sine B times the 1? So now I need to do this, right? I get sine A sine B. Plus, what happens when I multiply that by this? Well, the sine B's cancel, and I'm left with cos B sine A. And if you look very carefully on the bottom of the right-hand side, I have a sine A sine B, and I have a sine A sine B over here as well. Oh, that's interesting. It's not. Why is that not giving me? Oh, my mistake. We don't have a sine A left over here on the bottom, do we? Because what happens when we multiply this sine A, sine B times this whole thing is both signs cancel, and you're left with cos A, cos B. So we have cos B, cos A, and you can see that that is also here. So turns out not nearly as many moving parts as I thought, but still quite slippery, right? Because you're dealing with sines and cosines, you're dealing with A's and B's.